Hello everyone and welcome to this new video where we discuss physics and mathematics on the board. So today what we are going to discuss, and hopefully quite quickly, is basically a very simple technique to explain why there is a ground state, or basically a stability of matter in a sense that is non-zero in quantum mechanics, and essentially to explain this almost from entirely what we know from classical mechanics, and then applying to it Heisenberg uncertainty relations. And out of this, we actually get the ground state, and in fact here, the exact ground state energy for a harmonic oscillator. In the next kind of upcoming video, I will also try to apply this to a hydrogen atom to explain how we can actually get the energy of a hydrogen atom in the ground state. But we'll see that there are a bit more caveats to this particular derivation. Okay, so basically that's what we are going to do today. Right, so on this side of the board, I kind of summarizing the basic stuff that people learn in their high school course, let's say in mechanics and harmonic oscillator, but also in the case of um, um, more advanced levels, so probably first or second year university level as well. Here, because I'm talking about Hamiltonian dynamics, I'm starting from Hamiltonian, so that's more related, let's say, to quantum mechanics. However, you can feel free to start from the Newton's second law, and that would do exactly the same thing as well. Now, what matters is that we have a one-dimensional harmonic oscillator, fair enough, and then we've got this particular Hamiltonian. So essentially, that's the energy in the system. Now, whatever particular strategy you intend to use, you can actually even start from that energy and require it to be constant, and you're going to actually get the corresponding equations of motion if you want to. So what you would get anyway, regardless of the path you actually take, is this equation here. So p dot, so the time derivative of p is minus kx, and x dot is p over m. Okay, so that's the traditional set of equations that can be replaced, by the way, if you substitute here p as being x dot times m, you can substitute there and you will get basically ma is equal to minus kx, which is F equal ma. So, we can always fall back onto Newton if you feel more comfortable there. So the solutions for that, here I'm not going to provide the general solution, I'm just going to provide the solution, a solution that is simply easy to work with for what I want to do. The results I'm going to present here do not depend on the initial condition, but here I'm just selecting one just for the sake of illustration, if you will. So here the solution I'm actually setting is x of t is equal to x naught times cosine omega t, and p of t is equal to minus omega x naught m sine omega t, where omega is the natural frequency of oscillation, such that omega squared is k over m. Okay, so that's the period of oscillation for an oscillator, which is independent of the essentially the extent to which you had, for example, the value of x naught, for example. So how far you extended or compressed the initial spring. Now, usually, I think at the level of high school, that's kind of roughly where it stops. And then in some more advanced courses, you may also look at time averages. Okay, and these time averages are represented here by these symbols. So here, this is the time average of the variable x, and here of the variable p, when looked over a single period. And the period usually would be denoted uppercase t, but it's basically 2 pi over omega. So that's why I'm using here omega over 2 pi. That's 1 over t. And then here, this is 0 to 2 pi omega over omega, which is basically t, the period of oscillation. And I'm simply integrating this. So that's, again, the time average of x of t, And as it turns out, because you've got a cosine here, when you integrate a cosine, in this particular case, you're actually going to get 0. Okay, and that's because over a single period, you've got as many peaks as you've got troughs. Okay, and so they cancel out because integrals are signed. So when you're below the 0, then you've got a negative contribution. When you're above, you've got a positive contribution. Okay, so that's why we actually get 0. From a symmetry point of view, that makes sense. If you've got something going back and forth like this, then essentially you expect the average position over time to be essentially 0. So that's what is going on here. Um, and then you can also find out upon calculating the expectation value of the square of this over 2m, so essentially of the kinetic energy, or the expectation value of the potential energy over a single period, that actually they are both equal. And they are equal to that particular value. That's just one of the ways you can present it, but essentially they are equal. And what it captures is the fact that there is conversion of potential energy into kinetic energy, and then potential energy again, etc. And so over time, you essentially have the same amount in both, okay, at least over a single period. So that's essentially, again, what these particular equations are describing to us. Okay, so that's what I consider to be kind of for granted in the classical case. And what we are going to look at now is basically how can we explain that when we try to look for the smallest energy possible, we end up with a non-zero value in quantum mechanics. And again, we are going to use something very simple, which is Heisenberg uncertainty relation. So the idea here is to say that in quantum mechanics, we've got Heisenberg uncertainty relation. And what they read for the problem is delta x, delta p need to be larger than or equal to h bar over 2. Okay, so that's what they read. Now, what we are going to define is basically we are going to call 0-point energy or ground state, or sometimes this is called vacuum energy, the situation where these inequalities are saturated. And so what we have is that delta x, delta p is equal to h bar over 2. Okay, so h bar, by the way, is the so-called reduced Planck constant. This is h over 2 pi, and h is the Planck constant. And so that's what we have. Okay, delta x, delta p is equal to h bar over 2. Now, the only thing I'm going to do here is, because I cannot basically go below that, okay, I cannot, have an energy such that this is not satisfied, because that's what these inequalities are for. There is a lower bound to the possibilities for delta x and delta p for the product to be something. Then I've got basically here an equation that is going to relate delta x to delta p. But as it turns out, I also have here an equation that relates the expectation value of p squared and the expectation value of x squared. As it turns out, the expectation value of x squared and p squared correspond to delta p squared and delta x squared. And the reason why is because the deltas here, maybe I can write it. So the delta x squared is going to be equal to the expectation value of x squared minus the expectation value of x squared. So that's equal to x squared. And then delta p squared is the expectation value of p minus the expectation value of p squared, minus the expectation value of p squared. And therefore, essentially, these are directly the delta p's. So what do I do with this? Well, here, as I said, you've got one equation, so you can write a second equation, which is the following, that delta x squared and then k over 2 is equal to p delta p squared and then over 2m. And so now you've got a set of equations, and you can simply try to solve these particular equations here. So let's see what we get out of this. So for example, I can substitute that delta x here is going to be equal to, so let me get this right. Yes, so we are going to get that delta x from this one. Delta x is equal to delta p. So it's equal to delta p divided by km, and then I've got the square root of it. Okay, so that's what I have from this equation. Delta x is equal to delta p divided by square root of k times m. And then what I do is that I substitute back into the other equation. So here, and then I actually put that over there. So I've got that delta p divided by square root of km, and that's actually now delta p squared is equal to h bar over 2. Okay, so I've got delta p squared and then divided by the square root of km is equal to h bar over 2. So then what I do is that I can put all of this together. So I've got that, therefore delta p squared is equal to h bar over 2 and then k m and then square root. So what does that give us? Well, it gives us that the expectation value of the energy is going to be equal, because remember they are the same here. So it's going to be equal to 2 times the kinetic energy. Okay. So so it's equal to 2 times the kinetic energy. So that's equal to 2 times delta p squared over 2m. And so here the factor 2's are going to cancel out. So 2 times again, because the kinetic and potential energy on average are the same. So it's 2 times basically the kinetic energy. And so I'm getting that h, and here I'm going to put 0 point to say that this is the quantum fluctuations, is going to be, here I've got h bar, so delta p squared is here. So I've got h bar over 2 k m, and then divided by m. And essentially this is h bar over 2 and then k over m and then square root of this. And so we end up with the formula that h 0 point, which is the lowest energy you can get in quantum mechanics because of the saturation of Heisenberg equality, is half of h bar omega. Okay, so this is actually explaining what is the origin of like this 0 point energy. It comes from the saturation of Heisenberg's inequalities, and essentially it's just saying, like, putting a constraint which gives us an additional equation to find out why is it that we've got some finite energy there and we can't basically go below this, and this is half h bar omega. Now the reason why this harmonic oscillator example is also super striking is because all of quantum field theory relies on describing every field as a sort of additions of different modes, and these modes satisfies the equations of a harmonic oscillator. And so each mode has a 0 point energy, which is basically half of h bar omega, and the omega corresponds to the corresponding mode of oscillation, okay, that we call photons or that we call electrons, whatever. Here it's more, that would be more pertinent for photons. So basically that's the idea. I hope this is something that you found interesting. I will, as I said, in a later video try to do something related to the hydrogen atom as well, but as you can see, the calculations and derivations are fairly straightforward, so I hope you enjoyed it. If you've got any questions, please do let me know, and otherwise see you in the next video.